Okay, so our next speaker, Antonio Traverso, he represents the local industry from Genoa. So probably you realize that Genoa is spread over the coastline. So naval industry, everything related to naval industry, marine technology, sea, everything is very important. So he works with the industry here, naval industries. He works for Cetena, it's a research center. They have local collaboration with Fincantieri. So, you know, probably if you work with this application, is a big company. They do those big cruise ships. So probably if you walk by the harbor today, there is a very big one there. So they do a lot of research. So he's the head of the research development unit in Cetena. And now my honor to introduce you. Okay, well, but pretty much the same, I will say. Okay. So I gave you a promotion online. So now you ask to your bosses, oh, look, OpenFOAM promote me. Okay, so yes, to you, thank you very much.
Good morning, everybody. Thank you, Joel. Thank you, the organizing committee, for the invitation. Let me briefly introduce my company. Cetena is a company of Fincantieri Group. It was born in 1962 and it counts 90 employers. Generally, we are technician graduated in engineers, physics or mathematics. And we develop our competence to support Fincantieri or other shipyards in ship designs. Our competence, our skill is grown up through the developing of research projects with the ministry, industry in the national and the European environment. These are our main activities. We basically are involved in research and innovation, and to provide engineering and consulting. This is basically my business unit, but we also support Fincantieri with experimental activities, generally the sea trials before delivering the ship. Then we have some digital products. For example, we built up a naval simulator for customized naval simulator for simulating different maneuvers of the ship. And then we dealt with transfer of technology, generally in behalf of Fincantieri, to help them to practice education and transfer technology. And the mission, basically the mission of my business unit, is to be a bridge between the basic research of the universe and of the university and the industry research of Fincantieri. Generally, our activity is to build up, to prepare numerical setup for simulation and to find out new ways of numerical simulation to apply in the industry design loop. Cetena performs numerical simulations since the early 80s. Of course, at that time, we did not use the codes we are used to use today. At that time, there were Fortran codes, single purpose code without graphical interface. And generally, the programs were written by the user himself. There was a strong software user interaction. And the output, of course, was not what we are used to see today. They were huge output files with lots of number and data. And of course, the post-processing was not even comparable to today's standards, as well as the hardware at that time. The computers used were mainframes with a single course, multi-user, and as large as a freezer or a telephone cabin. Nowadays, we have updated our software and our hardware. Today, we're using basically commercial software, namely ANSYS CFX, ANSYS Fluent, Star CCM Plus, and Helix Engis. But still, we develop, and we maintain some in-house codes. The commercial codes we use are, as you know, general VSCO-Flow solver, RANSE solvers, and our in-house codes are codes based on the potential flow theory. And in between, you see OpenFOAM, that is a viscous flow solver. That means that it belongs to the list on the left. But I place it in between because we make some customization of this software. We wrote some routines in cooperation with the local department of Naval Architect, and we use this software standalone or also coupled with some of our codes that you see listed on the right. And of course, we change also the hardware. This is our old cluster. The new one has filled up the rack, and we go much faster. Well, in ship design, CFD is very useful because numerical process gain more and more important in industrial application, above all in the naval industry, because there is a big difference between naval industry and other industries, such as, for example, automotive. In the naval industry, there is not, in the design phase, there is not the prototype phase. In automotive, you design a car, then you build up a prototype, and you made a test on the prototype. In the naval field, it's not possible. In the naval field, you design the ship and you build up the ship. Your prototype is the final result. So lots of tests, both experimental and both numerical simulation, must be done to ensure that the process goes at the end fine without any problems. This simulation enables for a throughout process. Understand this as it's possible to separate different parameters and to see their influence on the final result. In fact, when you make a numerical simulation, you can test several parameters. You can test the influence on the final results of every component of your project. And you can also have a look inside the work and to see an analysis of the process. In fact, if you perform a numerical simulation, you do something like a small film, a small movie that you can play again and again. And you can see from different point of view to see every aspect of the physical phenomenon you are studying. And of course, in ship design, numerical simulation serves as a tool for planning for a single production step to the whole process chain. And this is important because in ship design, even if there is a lot of experimental activities, this can match very well with numerical activity. There is not competition because before making a test, an experimental test, you perform generally several numerical tests to see that the final solution is the best, and then you have only to check that the final solution is the best, and you don't have bad surprises when you go to the experimental test. And also, in numerical simulation are important because sometimes in the lifetime of the ship, you have to make some refitting, you have to make some problem, you have to solve some problems, and in this case, a numerical simulation is essential because no experimental activity is possible in this phase of the life cycle of the ship. CFD simulation is CFD software are very versatile tools. There I use in lots of fields of manufacturing industry. And if you go on the web page of a software production, you see a lot of examples that spawn throughout a larger part of manufacturing industry. And this characteristics matches very well with the problems that we have in ship design, because ship is a very big thing, is something like a small floating town. So there are lots of problems to be solved, and most of them can be solved with the aid of CFD simulation of fluidodynamics analysis. And in fact, you see here only a few parts of the operation of the activities we are involved, and we use CFD for slow speed flow, like air conditioning, where buoyancy-driven flow are very important. But we also use CFD for evaluating the thermal shock of a missile launch on the ship, on a warship, where the flow is at a high Mach number. We reach Mach number of 1 or 2, of course. Then we use, of course, in water and in air for the optimization of appendage, the propeller designs, the appendages lines for optimization, and for everything that may be important to reach the best performance of the ship. CFD modeling technology is not perfect. Today, we have some problems to face and to solve, but it's still possible to improve. This is an important statement, and we will see this involvement in the next example. Nevertheless, even if the models are not perfect, the techniques are used to compare and understanding different solutions and modes of operation. The application of CFD is more and more important over the year. There is the versatility, the accuracy, and the user-friendliness offered by the software is increased, and now CFD has taken up by naval engineering community and is regularly employed in the most phases of the design, above all in the preliminary pre-contract design phase. Pre-contract design phase is very important in naval field because this is a phase of design before signing the contract. In that phase, you have to set some parameters. You have to check that some requirements will be fulfilled in the future, but you don't have budget enough to perform experimental tests. In this aim, we have developed several applications in this field that generally are aimed to reproduce the activity that are carried out in the towing tank in the experimental structure that are used in the general used by the naval architect. And for example, one of the first tests that the designer starts to perform at the very beginning is the characterization, the design of the shape of the ship hull, the form of the ship hulls. And it's important at that stage to compare different solutions for evaluating the resistance of the ship. That means having an idea of the power to install on board. These simulations generally in the past were carried out in a towing tank. Nowadays, most of these activities are carried out in a numerical towing tank with the CFD codes. Generally, we start with a towed simulation, and then sometimes we arrive up to the self-propulsion. That means that the ship, in this case, is moved by the propeller. At this phase of the design, the propeller is not modeled in its entirety with a real propeller, but with an actuator disc with body forces placed in the back that emulate the effects of the propeller. And the results, of course, are the wave resistance as well as the wave profile that helps the designer to compare different solutions of his ships. Also, the appendage resistance is important because most of ships have appendages like rudders, fins, bilge keels, and so on. And in this case, also, we replace the towing tank experiments, and these are generally simple simulation, in fact, because the physics is not very complex in this case. But up to this stage of the simulation, we need to reach a good accuracy of the results, because these results are extremely important for the ship designers. That helps him to provide the right power to be installed on board. And so we have a great care of we take a great care to reach the best results in this kind of simulations. Of course, appendages must be aligned, and the alignment of appendages now is done generally by numerical methods. Also, experimental facilities have adopted this trend. Once 10 years ago, this approach was an experimental activity. Nowadays, appendage alignment is achieved generally in a numerical way. Of course, in this case, we use actuator disk model body forces to take into account the effects of the propeller. At this stage of the designs, we don't have an idea of the geometry of the propeller, so there is no point modeling a real propeller, but we have an idea of the thrust. And so we replace the thrust with the body, we replace the propeller with an equivalent body forces. And other tests that are generally performed in the early phase of ship designs are the test on the propeller. And on the propeller, there are several kinds of propeller, namely conventional propellers and also unconventional propellers, such as ducted propellers, thrusters, ducted thruster, maneuvering thruster, and so on. Well, for conventional propellers, generally after a first design, the designer has to check if thrust torques and efficiency of the propeller are satisfied. And in this case, for this kind of simulation, generally it's preferred to use BEM codes based on the potential flow theory. These codes run very fast and are quite reliable in this range of value. That means when the ship speed is quite high, near the design point, that is near the maximum of the efficiency. And at this point, these methods are still good, and they work very well. This BEM method starts failing when we reduce the speed of the ship and we go in this part of the curve where the viscous effects are predominant. And in this case, viscous flow approach is much more precise, and helps the designers to have an insight of the propeller performance also in that region. Of course, times in this case are very different, because computational time of a panel code is time of minutes, while computational time of viscous codes is in time of hour. Last Monday, I reproduced this curve with OpenFOAM in the morning. I start in the morning, and by the lunch I had these results. Anyway, even if the time gap is large, a viscous approach is important, because you have some more information. For example, the vortex detachment, and as I told you before, a more correct prediction of the propeller behavior in the zone of the low J. And of course, when things gets more complicated when we have non-standard situation. That means propeller in inclined flow, propeller in non-steady condition. In this way, in this case, a RANSE approach is much better, and of course is the most efficient approach. And in this case, of course, a steady state approach is not always possible, and we have to use an unsteady approach. But of course, these are unsteady cases, and it needs sometimes to be solved. Generally, we use a sliding. We use the approach with a sliding mesh where the zone of the propeller is modeled in the dedicated grid that rotates during the simulation. And As I pointed out before, the models we use are not sometimes are not developed enough, are not accurate enough. And in fact, one problem we face and we're still facing is the cavitation. Cavitation is very important in ship design and is very hard to handle with the numerical codes. This is an old picture. It represents the results of a workshop that was held 10 years ago, more or less, but I think it's very important as an example. In this case, we have the same propeller that works at the same point, that means the same rotation speed and same water speed, but with a different pressure of the tunnel to model two different cavitating conditions. In the case on the left, you see that most of the participants at the workshop reproduced very well the cavitation patterns. And on the right, you see another condition, and you see that in this condition, almost nobody except Procal, except this simulation predicted the cavitation in quite satisfactory way. In fact, there was an overestimation. That means that the models we are using now are not very efficient to reproduce all the cavitation phenomena that are possible. Strange enough that in this case, the best software is based on the potential flow as a panel method, not on the viscous flow. Anyway, cavitation is still important and must be studied because it's a problem. And now we approach this problem with the analysis of the pressure. For the propeller designers, sometimes is enough to have an idea of a cavitation inception. And in this case, the analysis of the pressure on the blades give an idea of the inception of the cavitation. And you know, if some cavitation develops over the propeller. This is a case study of a ducted propeller. In this case, the problem was that we have found some cavitation. We supposed that the cavitation was due to the detachment of vortex from the strut of the duct, and in fact, we see that as the vorticity moves from the duct to the propeller, there is a zone of low CP where that cavitation can be incepted. This is a study of cavitation inception. It is the solution of a cavitation problem without a cavitation model of the software, simply using the pressure as a marker for cavitation inception. Okay, another approach, another simulation that is interesting for the naval architect is the seakeeping, is the study of ship motion in waves. In this case, RANSE can be applied to evaluate the response of the ship in waves. Generally, these tests are carried out in a small basin in regular or irregular waves. And the output is a response operator that tells the designer how the ship's responds to a different sea state. In this case, generally, dedicated codes are used to evaluate the response operator, and generally these codes are based on potential flow model, potential flow theory. And a viscous approach of this problem is very complex because there are several problems to solve. First of all, there is the absence of symmetry because waves can arise from every direction. Of course, the simulation you have to do is unsteady because the phenomenon is clearly unsteady. There is the problem to model the wave pattern because generally waves tends to dissipate in a computational domain. So you have to to do a mesh particularly refined in the region of the free surface to avoid dissipating numerically the wave. And then we have also to take into account the fact that on the boundaries, waves can reflect and it's not appreciated. So you have to force some damping of the waves on the boundary to avoid reflection. This is a quite complicated setup. And of course, one can wonder if it is worth of not. Of course, if we are interested only in the wave motion, in the ship motion of the ship, its results are results of the two methods are more or less comparable. Results are more interesting if we are looking for the added resistance. If you want to know the increase of resistance of the ship due to moving in the wave field, in this case, a RANSE approach is more accurate than a potential flow approach. And but the real reason because these studies and this methodology are important is that sometimes there are some problems that are related to seakeeping, but these are not seakeeping problems. This is the case. It is the evaluation of the incoming water in the anchor box. In this case, you see that this phenomenon, this problem is ruled by the seakeeping, by the moving of the ship on the waves, but we are not interested in this case about how the ship moves, how the ship responds to the wave solicitation. But in this case, we are interested to see how much water enters the room and how to mitigate this phenomenon. So this is clearly a CFD simulation, but it's strongly influenced by the correct prediction of the ship waves, of the ship interaction with the waves. In this case, of course, results are good, even if a computational burden is very high and it needs some days of computational effort on our cluster to reach a convergence. Another problem we are trying now to solve with CFD is maneuvering. Generally, ship maneuvering is modeled with dedicated codes, as I showed you before on the first slides. We also have a naval simulator to simulate ship moving, but these simulators use, of course, simplified equations to run in real time, and some of these equations are ruled tuned up by several parameters. Now we have found that some of these parameters can be can be tuned more finely with the aid of a CFD simulation. So we perform some RANSE calculation over to reproduce some test and to find some of the parameters that are generally switched and are given to the simulator. For example, to take into account the fact of the hull over the rudder during the turning maneuver, or for example, to evaluate the forces over the hulls during the motion. And in this case, RANSE are both a validation tool as well as a support tool to derive some parameters needed to this software. Of course, the idea is to use one day a direct CFD approach of this phenomenon. That means the idea is to place the hull on the water, in the water, and then start the simulation with at the beginning with the captive motion, then with free motion, and to reproduce this reproduce the turning seal called the maneuvers that are requested. In this case, we have an idea, we have an answer of what happens around the hull, not only we have information about the maneuvering, but we have also some important information about the fluid dynamics below the ship that may be important and may generate sometimes problems. For example, vortex detachment and interaction of vortex detached from the fore to the aft body, and so on. And of course, this approach has been tested and used in in calm water, but the idea is also to use the same approach in the regular waters, in waves. And of course, this is an advanced topics. We are working on this problem. We have not reached any industrial results up to now, but at the present we are trying to model the circle of a ship in free running with the propeller and the rudders. And the idea is, as I told before, to use the CFD approach not for studying the maneuverability of a ship, but to study the effects of the maneuver over ship structure if there are some problems. Another use of another typical activity in naval field is the optimization. Optimization generally is done with a cycle. Starts from the choice of the definition of the problem, the definition of design space, the parameterization of in this case of the ship or of the propeller, and generally the solver, the CFD solver, is the tool used for the performance evaluation. At the very beginning of this activity, the main tool was a BAM solver because it's of course extremely faster. But we have found that thanks to the speed up of modern computers, also viscous flow codes can be very useful, at least to solve some particular problems. Of course, time is a problem in this case, because if you want to perform some optimization with a viscous flow solver, we need several days, also weeks of simulation. But we have found that sometimes this is worth of waiting this time, because if we have to study a local deformation, for example, a local bow deformation, in this case, an optimization cycle using a BAM method to evaluate the results takes 12 hours against the 5 days of a RANSE optimization. And in this case, the effort is not worth of, because the solution is more or less the same, and the results also is compared. The result in this case is the total resistance coefficient of the ship, and the results are very similar. But if we have to test a more complex optimization, where a global deformation of the hull is required, that means that you don't modify only the bow, but you modify also the aft of the ship. In this case, BAM method doesn't work very well, and so the results are strongly different. In this case, you see that the results are the final results are placed in different spots, and of course, above all, the final result, the response surface in one case has a total resistance coefficient that is much lower than the one derived with the BAM approach. Well, of course, okay. There is, of course, another important use of these tools is to study problems and cases where no experimental test can be performed. This is the case, for example, of the ship launch. This is the ship launch of Nave Trieste in the shipyard of Castellammare. Generally, a ship launch is studied with some empirical formula based on the story of the precedent or the foregoing launches in the shipyard. But in this case, the ship was larger and longer than any other ship, so it was out of range for the parameters known in that case. And of course, it's important. There are some data are important. Most of all, the stopping distance, because there is a key here that must be prevented from crashing, and also the clearance between the hull and the seabed is important to check, because we don't want that there is any crash between the appendages and the hull and the seabed. And this simulation has been carried out with the CFD codes, and we found that it works very well. That helps us to monitoring, to model very well all the features are interested, and the results are extremely interesting, even if the time requirement to perform such a simulation is extremely long, and the simulation are extremely complex. Another problems, more or less of the same time, is during the design of the top side of the ship to evaluate the interaction of the hull, for example, with a landing aircraft or with the aircraft during the takeoff. In this case, a simulation is important, is extremely complex, but it gives you lots of results. And as I told you before, this is a film of the phenomenon that you can see again and again, and you can spot out several details that are interesting. For example, if you want to see the effects of the takeoff over a radar, you can make some detailed analysis, and you have lots of information. But also in the second phase of the design, if you want to move, for example, or to place some electronic device, you have an idea, for example, of the temperature, and you find the place to place to place the equipment in a safe position. These simulations are also important because, for example, there are several air intakes, and another problem is to study the flow inside these intakes. This is a very simple problem indeed, because we know the mass flow, as we know the specification of the implants, but we don't know the temperature of the incoming air, because when the plane is landing or is taking off, there is a strong interaction of the hot flows. So in this case, we perform a dedicated post-processing of this simulation, placing a surface, placing a monitoring surface over the intakes. We derived from the simulation the time history of the temperature, and we supply this time history as a boundary condition at the inlet. So we found that we found the variation of the temperature at the intakes, and we can make our study with more accuracy to evaluate the efficiency of the cooling plant. And by the way, this is an important, there is an important consideration that I'd like to point out. I've talked about power computation and speed up of the computers, but we also need now storage, because one of the problems we are finding now is to storage the data. These simulation that I've seen are full-scale simulation and steady simulation that needs lots of data to be stored. And if computers are becoming more and more fast, storage is not increasing so fast as computer power. Anyway, just a few words to see that even if numerical methods are more and more complex and more efficient and can model more and more complex problem, sometimes it's helpful to simplify the problem. This is an old case when several years ago we had to evaluate the loads on pods due to the propeller effects. At that time, we didn't have power, computer power enough to model the propeller, the rotating propeller, and so we studied the motion and the thrust of the rotating propeller with the bend code, and we applied this code, this force to a CFD code to reach an evaluation of the load. Nowadays, we have we use again this approach. In this case, we have to see the effects of the propeller over the strut. In this case, of course, you can model, you have seen before in simulation, you can model the propeller, but in this case, you need lots of time to reach a convergence because we have an unsteady simulation. In this case, and of course, if you change the propeller, you have to change the mesh and run it again. In this case, we have evaluated the thrust of the propeller with the potential code. We have built up a grid for a steady state case, for a case without propeller, and then we mapped the results of the BEM simulation over the grid. So we have an unsteady simulation of a rotating propeller without any rotating grid, and in this case, results are much faster, and it takes 1 hour instead of 1 day to perform. Finally, we can invert the problem. Sometimes we have to study the behavior of the propeller behind the hull. Also, this case needs lots of time because the propeller is quite complicated, so we need some cells very, very small, and the hull is very large, so you need lots of cells ahead to model the hull and to produce the current wake where the propeller will operate. In this case, we are trying to model the wake with body forces and removing the hull and replace the hull with a disk or with body forces that reproduce the effects of the hull. In this case, an analysis of the rotating propeller in 5 days is reduced to an analysis of the propeller in 8 hours. The results are quite interesting. There is not a perfect agreement. This work is still in progress, and we have some discrepancy between the two approaches, but qualitatively the results are very promising. So we suppose that we are on the good way to find a solution. Well, to summarize, finally, what can I say? RANSE methods are widely used in ship design, not only as a protagonist, that means that you don't use RANSE only to solve a problem, but also as a supporting actors. That means that you use also RANSE to provide data for other kind of simulations. And powerful computers will allow RANSE method to complement BEM methods. BEM methods will live still long, I suppose, but now RANSE is becoming a good complement. RANSE method are very powerful. You can model the most complex problems, but time is precious. So if possible, let's keep us simple when we can. Thank you very much.
Hello. Thank you very much, Antonio, for beautiful presentation. Many applications that I didn't know about. So we have time for 2 questions. So if you have questions, please raise your hand. I have one quick question. How many of those applications are done with OpenFOAM? You see, can you use your microphone?
The applications are, can I turn back? Generally, all these applications, optimization, use OpenFOAM.
And that code.
Code. And all these applications, what we call virtual towing tank or virtual tunnel, These are developed with OpenFOAM. Most of these are developed with OpenFOAM. Generally, we have a philosophy. We use OpenFOAM for repetitive simulation. So standard simulation, vertical application that are set up very straightforward, and that have to be repeated several times. This is because we preserve from license engagement. Of course, for standalone application for solving problems in life cycle maintenance or to solve problems that arise, generally we use star CCM Plus or ANSYS CFX Fluent for supersonic flows, okay? Because as I told, the range is extremely wide.
Okay, thank you very much. Questions? Oh, okay, oh, there.
Thank you. I'll ask question faster to compensate for the work. I have two questions for you. The first one relates to CFD that is done in the pre-contract stage. And we usually find that most challenging because the geometry is not clear, the results need to be ready tomorrow, etc. So can you tell me what types of simulations you look for in the pre-contract stage?
Yes, generally ship resistance, calculation of resistance in calm water to evaluate the ship resistance, and of course to evaluate the power to install on board. This is the first, and the other is appendage resistance as well as appendage alignment. There is another kind of simulation that are not reported in this presentation that is generally for warships, is the smoke, the diffusion of smoke over the structure, because the optimization not optimization. The optimization is in the later part, but in the first part, an evaluation of the smoke impact of an evaluation of the smoke impact over the structure is extremely important in the pre-contract phase.
Thank you very much. We also get asked for maneuvering, crabbing, turning circle, that sort of thing. So the second question is about a big discussion in naval hydrodynamics today. So I have noticed that quite a lot of your simulations are on model scale. And at Wiki, we push towards full scale as much as possible because of fouling, EDFs, etc. What is your feeling of usefulness and difficulty between the two?
We must go toward full scale. It's unavoidable. We are moving toward the full scale for lots of simulation. For example, the simulation we have seen of the ship launch, of takeoff, and smokes are smoke air conditioning. Generally, most of these simulations are carried out in full scale, except the classical hydrodynamics. Strange enough, classical hydrodynamics is still related to the model scale. Unfortunately, this is a problem, of course, and we have to move toward the full scale. But to do this, we need, of course, more powerful computers, and also, I said it again, we need storage, because we are talking about computer power, CPU speed, but we must consider that the full-scale approach needs large amount of data to be stored. And as I show you very fast in the last slides, sometimes these results are taken out 1 year later to perform other simulations. So I believe that in the future there will be a particular care to the storage.
Thank you very much.
Oh,
Okay, thanks again to the speaker.